So again, my name is Sean Harvey. I'm a Technical Services Manager at Ansys, and it's my pleasure to be here. I'm also been using Ansys for 27 years, so I've really enjoyed the ride. And the most spectacular thing is to see where our technology has really come. So I'm not going to spend a lot of time on some of the corporate information. We're going to kind of get into some 6 focal points about Ansys. So I did just want to mention, Masha showed the slide up there, that Ansys is focused. This is what we do. We do simulation. You guys can see the slides up here. We have really high customer satisfaction. We're the largest, right? 3 times our revenue is 3 times that of the nearest competitor. So these are significant. So if you're not an Ansys customer, you happen to be in the room, probably Ansys is someone you might want to consider, being a partner with. Okay, so I put together these 6 bullet points. Why Ansys? All right, now I could think of a million reasons, but I focused on just 6 for this particular talk. Commitment to R&D, seamless workflow, multiphysics integrated platform, mapping external data. I know of us work with other tools, and we have to all coexist and work together. So that's part of that discussion. Unlimited control. So basically things that you saw Hari do a demonstration of our Ansys Workbench additive, right? And you can see that there was the ACT wizard that was shown in there. That gives us control to implement new things like additive very quickly into the mechanical user interface. So we really give the control to the user, and I'll get into all of those. And then I'm particularly proud of being a manager on the tech support team, outstanding technical support. So our commitment to R&D, if you take a look at this graph, it's pretty amazing. When Masha showed the slide earlier that we're investing $200+ million in 2017. That's just an astounding amount of money that's going back in. You can see Ansys is, financially very stable, a great company to be partnering with. And in fact, we've acquired so many companies and worked with so many new technologies that the graph there shows some of the companies, like on the ISIM side, on the meshing, and the CAD-DO, that one with the parameters and optimization. Then we've got CFX on computational fluid dynamics. Start working our way up the bottom of those flags in the tree. Electromagnetics we have in there, Apache for semiconductors, STRL for embedded software, even for composites. You can just see, even with the space claim, and then reaction design for, combustion modeling. And some of the newer ones here on the list that aren't even in that graph, with the latest one, 3D Sim, and even one that we're working with currently, which has, in the news that Ansys is acquiring, is Optis. So again, you can see we're putting a ton of money, like 1/5 of our revenues go back into R&D. So Ansys is really committed to our technology. Okay, so with that, I'll move on to actually, the talk is going to be more structural focused. But if there's anyone who's more interested in the other topics, when we have our open Q&A, we can try and field those as well. What I really wanted to point out in this slide is 48 years of technology in MAPDL. So Masha showed that in 1970, when Ansys was founded by John Swanson, basically since that day, the code that you see on the right has been evolving for 48 years. So for those who don't use Workbench Mechanical, you might be thinking, well, this mechanical, is it a new solver, is anything like that? I know those in the room who use it already know that behind the scenes, it is still running a code that's been in development for 48 years, and there's no change in the plan of making that go away. You're really just using a user interface to access that. Okay, so some of you, like I said, this is old hat, this news. But for some of you who don't, when someone says, I want to use mechanical, oh, is that good? Is that good as the APDL solution? Well, pretty much they're the same solver. Now, of course, you get different flavors of answers depending on how you use the tool. Whether we use nodal averaging and all these things can be different, but it is still the same tool. So once we write out that APDL file, and people can use mechanical and APDL however they want, you can go one way, which is just go ahead and work in APDL from that point on. You used your space claim to do your amazing CAD import and geometry cleanup, and you spit it out to an APDL file, and you want to work that way, fine. Bring it back in later. We give you the control to work how you wish, and you can always go back. So I know a lot of people who are in aerospace, traditionally are used to text file inputs, especially those who do a lot of work in Nastran, where I spent 10 years. A lot of text file inputs. We just make it easier to be able to do your pre, post, and solution in one environment, but still give you the control to use that. Okay. So just to set the record straight, because I know there can be confusion, that really this is, the same solver behind the scenes. Our meshing technology, I put in there fast with complete control. I've taught a lot of Ansys mechanical over the decades over the past decade to many people. And at first they think, well, it just creates a TET mesh, or I don't have the control that I need. If you drill down into it, we really do give a lot of control. There are lots of meshing technologies behind the scenes. In this fan blade example in the top right there, using things like our ISEM technology for your multi-zone meshing, things like that. There's some really great meshing technologies that have come over from our CFD acquisitions. So we've taken those meshing technologies and brought them into a common platform, Ansys meshing, inside of Workbench. So we also do work, of course, with beams and shells and tetrahedron. That helicopter example, it's just a demonstration, but there are hundreds of parts. Using parallel meshing, that meshes in less than a minute. So the talk is bringing your FEA into the 21st century, and many of you may say, well, I already know this. This is going to be broadcast to a larger audience. But I'll say to those who don't, really, this platform does give you the ability to innovate. Okay, so we're not creating one-and-done models where you go ahead and make a mesh, and then someone made a design change upstream, and now, what am I going to do? I got to start all over again because I've been working with a divorced mesh. So those who are in the field have to innovate very quickly. I overwhelmingly hear how much they appreciate the ability to work in this type of environment. Okay, large model HPC performance. An engine block model, I think it's almost 3 million degrees of freedom. It's got plasticity, it's got gasket elements, it's nonlinear. And if you look at what's happened at 18.2, you can see a tremendous amount of speed up in our scalability as we add number of cores. Okay, so one of the amazing things that we have done is kind of change our performance of our contact and change the capabilities of our contact to get this 3x speed up, which is pretty remarkable. So you can see historically folks have said that mechanical doesn't, FEA doesn't scale as well as CFD scales. But you can clearly see, given the right amount of hardware, we can definitely have really good scalability. So the solver rating over there tells you, basically how many times faster you would essentially be able to run that particular solution. So again, the first part of this talk is commitment to R&D, and this is absolutely Ansys's commitment to making sure that every release, pretty much things are running faster than they were before. And again, at 18.2, this was a big jump forward for this type of analysis. Linear dynamics is a very important analysis, whether it's just modal, whether it's harmonic, whether it's spectral, whether it's PSD. And we often have very large models. So what we have here in this example, right, this blade row model here, typically when we talk about meshing an HPC and solving an HPC, we're talking about domain decomposition. So we're taking different pieces and throwing it at the computer. With this frequency-based decomposition, you can actually get near linear scaling, so really good scalability, and you're actually throwing each frequency at the computer. So each compute node is actually solving for one of the frequencies. And when it's done with that frequency, it moves on to the next one. And this actually works out really well because you can get better load balancing. You can see some of the benefits of using this type of frequency-based decomposition. So again, as far as commitment to R&D in the area of linear dynamics, Ansys is very serious about being on par with all the other linear dynamic solvers, and just an indication of solving these big models using this new technology. Composites in aerospace, right? Composites is often very important, right? Lightweighting, lots of structures have composites. That's my area of expertise in composites. We've got composites technologies for decades. When I said 27 years ago, I was using a layered Ansys solid element that is still in Ansys today. So it's been in there, there's nothing new. I shouldn't say there's nothing new. It's not something we just added, but what we have done over the past 7 or 8 years is made it much easier to build complex solid models. So the model in the bottom right is actually a combustion chamber, and it's composite and it's layered. And we're using our ACP, Composite Prep Post, which is a great tool for this type of thing, where it builds a solid model the way you would lay it up. So essentially, you put in the geometry and you say, these are the plies, this is stacking sequence, and it goes ahead and creates that solid model geometry. And again, a composite model, like composite models are very complicated. And if I make any change to the geometry, it's going to go ahead and reflect in that ply layup. So with this whole workflow, I can make changes upstream and have them reflect downstream and even build the composite model. So they have contact in that model. I can drill down over here in the bottom left. You can drill down, look at your interlaminar stresses through the plies. We've got progressive, ply failure. We've got, damage models. And then your ply evaluations, your failure evaluations are up there. So again, Ansys has had the composite technologies, and we continue to evolve our composite technologies. Composites with fluid structure interaction. In aerospace and defense, many structures are going to be either sometimes radome covers, or they're going to be wings, or they're going to be something in a flow field, or it could be a wind blade. All types of, or propulsion systems often need fluid structure interaction. And again, we're making it really easy for those to run our CFD solvers, Fluent, CFX, and pipe that information through Workbench. So you can see over here how we're connecting the fluid flow into the setup. So in this model, this is a radome, and you can see the pressure contours on the radome, and then you can see the flow field of the aircraft below that. So again, we make it really easy to be able to take those CFD and the structural and the composite in one unified environment. And again, if I go back upstream to the very top cell of that ACP, and I change the geometry up here, that is going to go downstream and change the fluid mesh and also the structural mesh. So again, the time to be able to innovate with Ansys and these types of tools is dramatically faster than it is using conventional tools. So other areas where our commitment to R&D is the adaptive refinement. So being able to solve difficult, complex, nonlinear models. We get a lot of calls on support on, my mesh is overly distorted during the solution. How am I going to go ahead and solve this? And Ansys has really spent a lot of R&D effort to be able to do stuff like you can see here on the screen. So some of these examples, multi-body remeshing in this, this is like a torque drive device. These bars are cutting through, so like some manufacturing processes cutting through material. This is a glass blowing example. So really phenomenal. You wouldn't be able to do this without some type of adaptive remeshing. So that tetrahedral mesh is actually blowing out to fill that void. And again, these are all being done in our implicit MAPDL solver. There's no explicit solver in here. This is like a threading operation here. We're actually forming the threads, through working the material. And this is like a seal that's being pulled. And you can see the evolution of the mesh and the evolution of the stresses and the strains. So this evolution has taken place over the past about 6-7 years of development time to get to this point. Okay, fluid structure interaction. So in the previous case, I was showing kind of like a one-way fluid structure interaction. I know this isn't new, but we do make it easier working inside the Ansys environment to be able to take your CFD and couple it with the structure in a two-way environment. So, the heart valve example over there, where the flow is affecting the structure and the structure is affecting the flow, you need what we call system coupling. So the two are running in a synchronous solve to go ahead and solve this type of problem. But essentially, that's a Tetra Pak, and that's the behavior of the Tetra Pak. If you ever take a Tetra Pak or anything with a carton, and you start pouring fluid out of it, right, as the pressure drops, and all of a sudden the air has to come back in, and then you get the air bubble popping up, and the container pops open again. So again, those are the types of simulations that are possible. Okay, the next section here on seamless workflow. So Hari and both Brent touched upon, we have space claim, and I'm not going to spend a whole lot of time on space claim, but our CAD connectivity, once we have space claim, being able to bring in models from any of the CAD tools, and pretty much everything under the sun we can take into space claim and bring that down into our downstream tools. has been overwhelmingly positive by our customer base. So you can bring in pretty much anything, and then you can reverse engineer. You can go ahead and clean up. You can modify, put in holes, remove holes, do all kinds of changes before you go downstream to your FEA or CFD simulation. But we have bidirectional support. This is CAD neutral. Ansys is CAD neutral, so we work with all the flavors. And though it's not in this interface in Space Claim, I did want to bring up, and I know we're going to have a Q&A, like roundtable discussion, we do bring in Nastran. So again, if you have legacy Nastran models that you want to now bring in to do, let's say, FSI or something like that, we can bring in those types of models. And we will be making it much easier shortly to export the Nastran outside of mechanical. So you'll be able to take those Nastran models out of mechanical to say you have to integrate with, depending on what you're doing. Like if you're in space and you have to do a coupled loads analysis, be able to take that stuff in, we're going to have a solution for you guys for that. Okay, another thing to point out is, when we say here seamless workflow, we're able to do linear and nonlinear, so you don't have to switch from an implicit to an explicit. Everything is going to be in this environment. In fact, I'm just highlighting here, if we go ahead and see the red ones I highlight, there's a static, there's a transient, there's a modal, but everything that we put in that's structure related ends up in mechanical. So whether it's our multi-body dynamics or rigid body dynamics solver, or whether it is our explicit solver, they all have that common UI. So really, it makes it really easy for a person who is not familiar with maybe a new code to adapt to that new code or that new solution sequence that we're using. So they don't have to learn the new software. Again, the workflow stays the same. So they can be doing explicit, they can be doing rigid body dynamics, they can be doing transient, they can be doing harmonic PSD. It's all in the same environment. Ansys is physics-based simulation. So from the structural mechanics standpoint, we can do all kinds of things. We're just going to use this helicopter as an example, right? So for multiphysics, you might have an electric motor, an electromechanical coupling. So being able to connect those two together, which is very common for electrification. Ansys is used extensively between the Maxwell and the Ansys mechanical tool inside of Workbench. We'll be using it for, let's say, on the blades, stress and explicit dynamics. So here they have like a bird strike, a bird impact on the explicit dynamics. Vibration, so like I said before, it could be transient, it could be flutter, it could be harmonic analysis. Composite failure, here they're looking at things like rivet fatigue. This example, which kind of paints a picture of, again, multiphysics in an integrated environment. So our example, this is the Workbench workflow. Now I know there's a lot of stuff on there, but it's important to understand what each one of those is kind of doing. They're interconnected to a unified model upstream. So the objective here, is to look at the performance of an avionics enclosure. An avionics enclosure will have an environment that will include thermal environment, it'll have a vibration, structural environment, and we want to look at that from a unified point of view. So this is my mock-up of an avionics enclosure, right? It's just a box, it's a board inside that box. And one of the things we might want to understand is, how is the heating or the cooling, the ventilation of that box? Is there a fan? Is it natural convection? So I can look at things like do accurate prediction of my temperatures inside that avionics box. So in aerospace, this would be something that is, very common to look at something like this. And then from there, obviously, what would we do next? We solve for the conjugate heat transfer on the CFD and the mechanical, and then we'll solve for the thermal stress. Okay, and then, so once we have the thermal stresses, and then another thing we'll do is, in aerospace, right, we often have all kinds of load conditions from crash loads, all the inertial loads, takeoff loads. So you can look at X number of Gs, vertical, lateral, fore and aft. So I'm looking at some of the deflections of the board. And then we'll look at our natural frequencies, the modal, and then I'll look into harmonic potentially. So, harmonic, if it's going to be sitting there, and we're going to make sure we're not going to get the thing resonating at a periodic frequency of the rotor blade or whatever your excitation frequency is. So we'll be able to look at the harmonic, and we'll be able to look at things like transient structural. So if I want to do like a very short burst impulse and see the response, so being able to do impact and transient. So what you can see from here, if I was now to go back to the beginning of the schematic, and update my geometry. Like, let's say I'm going to move the location of the board or something like that. All I have to do is hit the update button on the project, and then this conjugate heat transfer and ice pack will run, mechanical will run, all of these downstream simulations will run. Okay. So that gives us the idea of how to do that type of example. Here's another really great example. This is a landing gear example. So if we look at the top, we'll be looking at things like from pre-processing. So you get a model, and you got to work with that model or change that model. Aerodynamic performance or composite evaluation, even things like radar cross-signature, aeroelasticity, rigid body dynamics, all those are in this particular model example that we've put together. So on the pre-processing side, if I just click on here, this is inside Space Claim. So I bring in this CAD. This was given to me, and I want to say, OK, what if I go ahead and I change this mount or this bracket, or I change the shape of a part of the geometry? I can easily go in, and make those changes. So this is CAD from any of our CAD tools, right? You guys, if folks haven't seen this, that in itself is pretty awesome feature for those of us who have to often work with CAD from other people. As an analyst, we want to go ahead and make the changes, and not have to go back and ask that guy. We can go in and make these types of changes. So you could go ahead, and in this example, we're taking that door, and then we're running lots of simulations. I don't have all the details here, but you can see we have aerodynamic performance. So we actually have the fluid flow on the aircraft, which is this part of it here. So if you take a look at it, you'll see the eddy shedding forming off of that. And in the top of that, you can kind of get an idea that there is some fluid flow taking place around the door. The pressures are here on the landing gear door, so we're mapping that directly. We're also running HFSS to look at the radar cross-section signature of the aircraft. So what happens if a part is bigger or smaller, or where I place my parts? Is it going to change what my RCS looks like? So we have that graph down here. And then over here, the rigid body dynamics. So if we want to look at things like, all right, here's a landing gear. How does it articulate? And how do we drive that with our system simulation software up here, Simplorer? So here you can actually have, our system level models. And I know people have heard about digital twin and reduced order modeling. But that's the same system level modeling tool that we use to drive our rigid body dynamic solver. And at the back end of this, I've taken it out to the durability. So predicting the life and lifing on the part. Now you could go one step further in this demonstration. I don't have it shown, but you could do things like, what is the digital twin? So, looking at predicting, in-service life of a part is something that's, available. Okay, another thing that's really important, and I don't want to underemphasize this, because on support, we see lots of people trying to get data into Ansys, and many of them still don't know. So, if there's anyone in the audience here who hasn't seen this, then it's pretty eye-opening. We really make it easy to get data in and out from whatever tool you're using. And we've really expanded the way that you can bring this data in. So you shouldn't have to struggle to bring in data from other solvers. So in the top right, you can see the many types of data types, from temperature and pressure and heat transfer coefficient and heat flux, heat generation. We've added in things like initial stress, initial strain. The point being is that Ansys is pretty open to take in whatever you have from your other runs. So if you have initial stresses and strains, or you have temperatures, or you have in-house codes, getting that into Ansys to be able to do downstream simulations is just using this thing called external data. So external data uses a spatial mapping of your results, and it does a mapping onto your part. So you can see here in the bottom right a preview. So after you bring in that data, you can then preview it on your model and say, OK, how is that mapping? And there's a whole slew of mapping options, and how that data gets mapped and validated so you can actually see what is the best mapping I'm going to use for my particular simulation. So again, I know in an ideal world, everyone's going to use Ansys for the CFD, the EMAG. But in the real world, oftentimes you have to use another tool, obviously. And external data is a phenomenal capability to be able to get that data into Ansys Mechanical, make it really easy. So most of the time it's a CSV file. You can go ahead and bring this in. I see people still on support writing scripts, to bring in data from third party, and then you say, show them this and like, wow, I had no idea Ansys had that capability. So it makes it really nice to be able to bring in that data. Okay, the next section on unlimited control, it really shows the amount of support that's going behind Ansys right now. So if anyone in the room hasn't been to our Ansys App Store, whether you're an Ansys user or not, I encourage you to do so because this was just started a little while back, and already we have 280 apps that have been created. Now, an app can be anything as simple as I want to simplify the type of structural analysis I do on a day-to-day basis, or incorporate a feature that hasn't been incorporated. For example, what Hari was showing with the 3D printing is using our Ansys Customization Toolkit, or ACT, to enable you to control mechanical and change the user interface, put in wizards, be able to control things like that. So if there's a process that you're doing at your company that other people have to replicate, you can use the ACT. But you can also go to the store and look through the 280 to see if someone hasn't already done it for you. And the list it's pretty impressive at what people have put up there. Okay. In addition to that, so you have the ability to use other people's apps. You can create your own through ACT, so you can extend it very easily. And remember, you always have control with APDL. I didn't really get into it, but anything in mechanical that you want to introduce as an APDL, you can put in command objects and go ahead and add to it. Okay, so the last part here is on technical support. So I think this is important because I know our tools, as easy as they are to use, I know on a daily basis we get lots of calls. And a lot of those calls are just, what's the best way to go about doing this? And we're there to help you. If you take a look at this graph, since 2011, because of the drive for making customer support a business driver in Ansys, because we know this affects you and your use of the tool, you can see that we've invested a lot to bring up our Ansys percent satisfied customers up to about 94% in North America. I can tell you hands down from hearing from all the people that we talk to, this is very important to them. I see every customer satisfaction survey that comes in. And what I'm hearing from the field is that our competitors are not taking customer satisfaction as important as Ansys is. So when you're working with Ansys, please know that you have a really big team of people. In North America, we have over 60 people on a daily basis covering mechanical, fluids, electromagnetics, and systems installation. So we've got 60 people, right now there to help. And again, it's as much as the software is a great product and all of our development, all that, customer satisfaction and getting help when you need it is what tech support is there for. So this brings me back to the beginning slide. Okay, I know I had 6 bullet points. Why Ansys? So again, I could put so many on here. Hopefully you see that having Ansys and being part of a community of people who really want to innovate, because our customers want to innovate. So if you want to be part of that community, you want to really be with Ansys.